Vafa is a Hollis professor of mathematics and natural philosophy and professor of physics here at Harvard. And he will give us a review on the string theory landscape and Swampland.
Okay, thank you very much for the invitation. It's a great pleasure to give a talk here at BHI. Actually, the topic I'm going to talk is actually motivated by black holes. So the whole thing is about black holes. But then a little bit extension to the rest of the universe will also come at the end of the talk. So I think it's probably this kind of topic, I think, is actually surprisingly deeply connected to black holes in a way we don't understand. So this is, I think, a lot of the motivation for the talk I'm giving you, as you will see, is related to black holes. So string theory is giving us a consistent framework which unifies quantum gravity and Einstein's theory of gravity, and it's highly non-trivial accomplishment. I would say it's the only one, really, the only main show in town. So we have to kind of see as much as we can learn from this theory. As you know, that means that you replace point particles with strings, extended objects, and of course later we learned that it means that it could be more than just one-dimensional, it could be general extended objects. But always we need extended objects to deal with this theory. And the interactions are these beautiful geometrical properties of strings going together, two strings joining into one, and somehow the singularities of point particle theory, where usually when they get together they might be a source of singularities, when a bunch of them come together, is smoothed out because of the fact it's extended. So that's one of the main lessons, is the extended nature of it. And it resolves inconsistency between quantum theory of gravity and quantum theory and gravity, and that's one of the main claims to fame for string theory, which is why we really love this theory a lot. But there are some bizarre features or interesting features, and one of them is the extra dimensions. And it is the prediction that we need extra dimensions beyond the 3D spatial dimensions at one time. And these kind of things are okay as long as you have a solution of what we do with these extra dimensions. And the typical attitude is, well, you can take them to be tiny, and if it's tiny enough, you can't see them in experiments, so therefore you can kind of average over them, so it's not a problem. Okay, this is the usual quote-unquote compactification. We take the extra direction instead of being as big as the regular dimensions. We take the extra dimensions to be tiny compared to the macroscopic dimensions. So we think we have 3 macroscopic directions, and whatever else, 6 extra spatial tiny directions like circles or spheres or other things like Calabi-Yau. So in general we don't know, and so you can think of this picture of this as to remind you that every point in space, every point in macroscopic space, you think of having this extra other thing which is in a different dimension, and it's kind of so tiny you just ignore it and you just think about the macroscopic spaces you see, and it's just there for making the theory consistent. And that's all. Well, not quite all. It turns out that precise properties of this, what this geometry is, and the detailed properties translate to properties of, this is just a caricature of what kind of things you can have. It's much more colorful than this, the actual study of it.
What are we looking at?
You're looking at shapes here, this like string, no, I'm just kidding. So this is like, this is supposed to be like Calabi-Yau, I'm just saying,
What does it mean?
This means that you have a 6-dimensional manifold, and you can take the slices of it this way or that way and so on. So you can take pictures of it. People come up with these kind of pictures. Don't worry about it too much. So the physical properties observed in 3+1 dimensions depends on the choice of the compact tiny space. Number of forces, particles, and their masses, etc., all depend on the detailed properties. So even though you don't directly measure the short distance property of what's going on in these tiny dimensions, the large distance properties get translated to topological aspects of this space. So there's some aspects of it which actually filters and comes to be realized in our universe. Like in the context that we live in, to get, for example, the standard model with the generations we want, you have to go and tune the properties of the manifold and all that to be quite right to give you exactly like 3 generations, like this gauge group and so on. All depends on the details of what the 6 tiny space might be. Now, there are a vast number of allowed tiny spaces which you can have, and therefore this gives you a vast number of possible universes. And this possible universes is called the string theory landscape in the abstract. So the fact that there are consistent solutions of string theory for a huge variety of 6-dimensional space is, by now, I think, a well-established thing. Nobody in string theory community doubts that's well-established, including the simple periodic box kind of example, like what we call torus. So we take 6 periodic directions. That's the simplest example. That's perfect for good landscape. It's not our universe, but it certainly belongs to a would-be universe. So the question of what it is that is our universe will be actually to find among these huge number of choices what it is that you could have. Now, so if you think about the extra space as this, like this torus, in this case, like this donut-shaped object, and the blue one as a macroscopic space, you have extended objects like strings and membranes and other things that can wrap around the non-trivial cycles of this geometry. And as far as the rest of the space looks like, it looks like a given point. In other words, at each point, you can choose the corresponding tiny space and wrap around the cycle of that point. Or if you are over here, there's a corresponding two-dimensional torus on top of that one, you could wrap around that one. So as far as the space looks like, these correspond to point particles depending on what you do. So in other words, these extended objects become just point particles. But the hidden degree of freedom of them is still there in the structure of what they do in the extra directions. So is it like that one, or is it the other way, and so on, and they correspond to different particles with different properties. I better watch out. So, otherwise, you will incur some losses here in the you don't want to have a hole in this. Okay, anyway, so let's go. So now this leads to the vast string landscape. This is the landscape that you would think.
But I'm missing something.
Yes?
If in the old days a theory predicted a lot of possibilities, and we knew about one, we would say the other ones do not exist. Now
That's
we
not what
say
we
the
say.
other ones exist.
Yes, we say all of them exist
Why?
because all of them are consistent in that theory.
Yeah, but maybe the theory is not the full
No,
theory.
the theory as a mathematical framework is self-consistent. You could say, is that our physics or not? That's a different question. I will come to that question. But the idea of string theory landscape is that there are many possible universes. How we ended up with us, with our universe, is still not answered. But that's a question we need to ask at some level. But it is like saying that, okay, we have the galaxy in this. Let me give you an example in Newtonian physics where you see what I'm saying. We could imagine that the sun is shifted by 1 meter and everything else is doing similar and shifted by 1 meter compared to the rest of the galaxy. That's a different universe. Well, okay, but the laws of the Newton didn't change.
Right.
Why do we study that? Well, it's not going to change the laws, right? So in other words, what I'm saying is that that's in the context of string theory, there are different choices will give you different ones. Which one we are in is of course just one of them. That's true. Why are we not in the other ones? We could ask the question of what is the reason, and that's a meta questions in some cases.
But they might not exist. You are saying they exist, but we are not in them. They might not
They are
exist.
mathematically consistent.
Yeah, but mathematics is not physics.
Mathematics
It's different.
Well, we don't know what physics is. namely, there is a universe we live in, which we could call physical, and if you define that to be only physical thing, you're just ruling out everything else.
Yeah.
String theory says you have to have a broader definition. That's the paradigm of string theory. You have a broader definition of what the universe is. We live in one universe, and there are other choices. Meaning, if you take mathematical consistency as a paradigm, which we do, then physical reality is consistent with that in many different versions. And ours is just one version. Let me explain it a little better, perhaps. Take SU3 gauge symmetry. Can you imagine SU4 doesn't exist? Well, yeah, it doesn't exist because you have QCD, you don't have SU4. Is it consistent to talk about it? No, it's not. Of course it's consistent. You wouldn't say SU4 is a bad physics. You would just say it's not our physics. If you accept that answer, then this is the same answer. Unless you say no, SU4 is not physics anymore.
That's what I was.
Okay, no, I think then your teachers are very strict. Namely, we wouldn't say that. We would say that our universe is SU3, and yes, SU2 is a similar one, and SU4 is a similar one, but our universe is SU3. And sometimes SU2 is easier than SU3, so you study SU2, and you learn some lessons, say, okay, this looks like it. Let's see what does it teach about SU3, which is our universe. That's the way we were taught. We wouldn't say, I wouldn't study toy models. The word toy model is a well-nourished concept in physics. It's not new to us. It's not new to string theory. If you wish, these other universes you can view as toy model for our universe. That's the easy way to think about it. To rule them out, just I don't want to study because our universe is not this, I think it's just saying I want to throw out everything except SU3 gauge group, and that's a bit too narrow. So anyhow, you have this view of all these possible choices, each one giving its own landscape, and indeed, as it was discussed, our universe is just one of them. And we are one of these points, and we have to understand what we are, but there's just one point we are corresponding to. So going from compactification choices to the landscape is too cumbersome because there's a huge number of consistent choices. This raises the question, can we just reverse this and pick a consistent looking 3+1 dimensional theory and not worry about where we got it from and just deal with the physics of it? In other words, if the string theory is at the end of it giving us an effective 3+1 dimensional theory and there's such a huge number of choices and basically almost infinite, just pick a consistent looking 3+1 dimensional theory and let the string theorist who's bored figure out which compactification geometry will lead to it. Okay? That would be one possible way of saying, therefore it doesn't teach you anything. If that's the case, if this is indeed the case, that string theory gives you everything that you want in consistently 3+1 dimensional looking, then you haven't really learned much from string theory because you just say, okay, thank you very much, I don't need you guys. I'll just write down my effective theory and you go and figure out in your office what compactification of Calabi will give you that, but that's not useful for me. I'm just interested in 3+1 dimensional physics. I want to do measurements in this universe, therefore forget about what you're going to tell me. So that actually would be a very bad news for string theory. Therefore, we ask the question, can any imaginable, at least consistent looking imaginable universe be realized by some kind of a string compactification? The answer turns out to be no, and that's the important point here. That is, not all the consistent looking theories that you can think of in 3+1 dimension actually can arise in string theory. Now you might say,
when you say a theory in 3+1, you mean a gravitational theory like
yes,
Einstein's field equation,
yes.
or?
So the way we usually do is this: we usually take a Lagrangian, a field theory like Yang-Mills theory with some matter, and we say, quote unquote, couple it to gravity. It turns out for almost everything you pick, coupled to gravity doesn't work. So in fact, the statement is the opposite. The attitude like couple it to gravity usually doesn't work. Only in very rare cases it works, and these are the landscape points. The question is to understand exactly what are these conditions that make it work. That's the question. Now, this is good news for string theory because otherwise there will be zero predictive power. That is, you can just take anything you want and just declare it's fine. There will be nothing you can do to rule it out. There's nothing. So in other words, most consistent looking theories in 3+1 dimension are actually not consistent. As a quantum theory of gravity, even though classical gravity with those fields makes sense. Now, when I say they're not consistent, I don't mean like, oh yeah, there are anomalies and you just forgot about anomalies, or there's some silly thing you forgot about. No, I'm just saying, once you take into account everything that you can think of in terms of low energy physics, they're fine with it, but still the theory doesn't make sense. And these turn out to be the point that we want to declare those theories. The theories that look otherwise perfectly fine, but actually do not complete to a consistent quantum theory of gravity, we call them as to belong to the Swampland. So indeed, most of the points that you look around is in terms of the low energy degrees of freedom of the Lagrangians, which are consistent looking, belong to the Swampland. So the criteria of which ones, how do you distinguish? What is the universality class of the quantum gravity is the main question of what we want to do.
What is it that they violate?
So I will come to it. So I'm going to give you some examples of what they violate. And it turns out invariably they relate to black holes. So black hole physics is precisely one of the constraining aspects of this whole thing, and which is why this is actually the right place to talk about this stuff, which actually gives you an insight about what it is defines the universality class of quantum gravity. Yes?
Quantum gravity is string theory.
I'm defining it to be string theory or M theory or whatever is that whole universe of possibilities you understand in string theory. Yes.
So why are you limiting yourself just to string theory?
Because that's the only ones I know of. But
Yeah,
of course,
but
other people can study things that they
someone with
understand.
better imagination will come up with a bigger.
They should do better work than I do. What can I say? I'm not saying nobody can do better work than I do, but I can only do what I can. I'm not precluding anybody else. Everybody's welcome. Door is open. But the road is long, as we say. Okay. Anyhow, so what distinguishes landscape from the swampland? What are these consistency conditions, and what we know? The answer to this is we don't know. I wish I could tell you that if you A, B, C, and D are satisfied, you're done. You can go home. I don't know. We don't know. How do we know that there are any consistency conditions? Well, I will try to explain why we are relatively confident that there are, and I'll give you some examples of why we think they are and how they work. Meanwhile, there are some of them we are more sure about, and there are some of them we are not as sure about, and so on. I'm going to tell you a variety of things that we have come up with. So I told you already that not all consistent theories arise from string theory. Some of them can be captured by some principles, and at least some of these Swampland conditions can be motivated by black hole physics. And then these lead to some specific predictions for our universe. I'll try to tell you some of them. Okay, so I already told you this. So in string theory, I told you about 10, but sometimes we have other versions like M theory or F theory where the dimension can go up and so forth. We start with a higher dimensional theory typically, and we go through compactification to a lower dimensional theory via an intermediate space, a manifold, a Calabi-Yau or some such space, and this gives you a d-dimensional physics. And there are a huge number of possible M's you can choose, and that's the huge number I already told you about. And as I told you, the M's do not give you all possible effective theories. Out of the space of all the effective theories, you get a very small island, which we are calling the landscape. And so here, I'm going to talk about these particular criteria for the landscape versus the swampland and try to motivate why they arise. The first criteria I'm going to tell you about is the only allowed continuous symmetries are gauge symmetries. So one could have imagined having, a quantum field theory with a global symmetry. No problem, there's easy to write down, and you can say couple it to gravity. You can do that. It turns out that global symmetry, either it's broken, or if it's not broken, it better be gauged. It cannot be, there cannot be any exact global symmetries in string theory or quantum theory of gravity. All gauge charges appear in the spectrum. The spectrum is complete. That is, suppose you have a U1 gauge theory, and only the even electric charges appear, but the odd ones are missing. Or if you have a lattice of a U1 times a U1 theory, some particular sublattice of charges appear, but the other ones are missing. That cannot happen. All the charges are occupied by some states. Of course, you can easily imagine quantum field theories which are missing the odd charges. There's no problem with OPEs or any principles of quantum field theory. So this is sometimes called completeness of a spectrum.
Are you saying that that's an assumption?
No, I'm going to explain
No,
why we
to
believe
show that these are all
show is a
true
stronger
statements.
statement.
Okay.
I would not claim to show anything in this talk in the sense of showing the rigorous. I'll try to give evidence that these are actually the case.
These are the case. Okay.
With varying degree of certainties. Yes. The range of fields, so if you have scalar fields in the theory, their range is finite. Now you can imagine a scalar field, and in general you might think that the range could be from minus infinity to plus infinity. Here we want to say that that's not the case. That means that if you're interested in a given consistent effective field theory, the field is cut off roughly at the Planck's distance in field space. The theory must admit light higher dimensional objects. Any theory of quantum gravity, regardless of whether it's string theory or not, I will try to argue from these principles, and in particular from principle 3, you deduce that they must necessarily have extended objects. So the extended object, which looks like a bizarre feature of string theory, and these properties may follow from it, can reverse the order. This property 3, I will show, implies property 4. So the fact that the ranges of the fields are finite gets related to the fact that they must admit extended objects in the theory.
So it's not an independent group.
That's right. Even though I stated independently, you could view it as derivative, with an argument that I will try to sketch. Gravity is always the weakest force. What does that mean? Well, and we know around us that gravity is electric, for example, repulsion between electrons is much stronger than attraction between them. And you might think that this is a peculiarity of our universe, that you could easily imagine universes where the gravity, the mass of the electron, was much bigger, and therefore its electric repulsion was much smaller. That belongs to the Swampland, the claim is. Gravity is always the weakest force, just like our universe.
Sorry, why is it like that?
I'm going to come
Goes
to.
higher
I'm going to. This is the outline of the things I'm going to talk about. I'm not expecting these all to be obvious or clear or anything. I'm just stating, and then I'll come one by one to them. This 5 is point 5 is called the weak gravity conjecture, and I will give evidence for it. And finally, the consequences for cosmology and the Sitter space. This is a more recent work. This is the part that's actually still people are debating whether it's correct criteria or not, and there are various hot debates going on in this area. And I will also say what
You want to avoid controversy by not saying inflation, you're just saying de Sitter space.
No, I will talk about inflation. Don't worry. I'm not
It's
worried.
inflation.
I don't worry about controversy as long as we spell our assumption. I don't want to pick a fight, nor I'm trying to avoid the discussion of science. So, I don't have any shyness. I'll talk about it. Don't worry. So-
Cosmological constant, if it's possible that in landscape it also be negative,
Yeah.
then you have anti-de Sitter.
Yes, those are good ones. It turns out.
But then this is not belong to
No,
the.
no. I'm just saying there will be some statements we can make about would be de Sitter space. I'm in fact going to say there is some conjecture which forbids de Sitter space. I haven't told you that. But anti-de Sitter spaces are perfectly fine, and we have a huge number of examples in string theory. Okay, so here I guess I don't have to say this in this audience, but some basic facts about black holes. You fix a charge and a mass, and then as long as m is bigger than q, there is a nice classical black hole spherical symmetric. Well, in this case, I'm forgetting about rotation, but let's forget about it for now. You have a nice spherical symmetric black hole with that charge, and the extreme case is m equals to q. That is what's called the extremal black hole, the Rice-Nordstrom black hole. All black holes have an event horizon where if anything crosses it, cannot get out. Okay. So this is written for an audience, I guess, which is a little bit less familiar with black holes, but then let me just continue. Black holes have thermodynamical properties, and in particular, they have an entropy given by the area of the horizon over 4, as Bekenstein and Hawking argued. So that means the number of degrees of freedom of the black hole of a given mass and charge is exponential of the quarter of the area in Planck units. Now, this point 3, all black holes disappear by gradually emitting elementary particles. Now, certainly this is the case for non-extremal ones. That is certainly the Bekenstein-Hawking kind of picture for the thermodynamics of black hole. The extremal case is not clear. The extremal case is the case where there's borderline in their computation, and you begin to whether you trust the computation there in that context or not. It turns out that there are cases in string theory where it doesn't decay, as if it's supersymmetric extremal. But there's no example of this non-supersymmetric version of black holes that we know of in string theory, which is extremal and stable. So even the extremal ones, even the would-be extremal or approximately extremal ones that you try to approach extremality, will always decay in the context of string theory, and if you don't have supersymmetry. That's at least all the examples we know of, and I'm going to take that as a principle, that all black holes decay unless they are BPS and supersymmetric, which is very rare occasion. Okay, so now this was a quick set of assumptions or a review of black holes, and so I come to criteria 1. I said only gauge symmetries are in the theory. There are no global symmetries allowed. Well, there are various arguments, but this is the heuristic argument, and this is related to black holes. This is one of the original reasons people argued about the global symmetries not being there. Suppose there's a global symmetry, and you have some charge like electron number. Suppose the electron was not gauged. Suppose there was just electron number, that was a conserved quantity, and you throw you have a black hole, and you throw electron in a black hole, 1, 2, 3, 4, etc. So you know the black hole has 4 electrons and so on. But then it emits radiation and so on, and the information of how much there is goes away because it's not gauge force, there's no long-range force coming out, so that information of what is inside, in terms of electric field and all that, is lacking if it's a global symmetry. And by the time the black hole disappears, it emits equal amount of one number of anti-electrons, and so the net number wouldn't be changing by the black hole evaporation, and therefore you violate that electron number. So if you have a global symmetry which is not gauged, therefore black hole is a mechanism at least to violate it. That means quantum gravity cannot have a global symmetry that is not either gauged or approximate. So we can have approximate symmetries, but not an exact symmetry in the context of quantum gravity. Now this heuristic argument, admittedly, is a bit heuristic, and people have tried to make it more precise in various contexts, but I won't say what details of the context. This heuristic argument is, of course, backed by all the examples we know of in string theory. There's no example in string theory where global symmetry arises without gauge symmetry, or approximate symmetries can be, but not exact global symmetries. And why is that? Well, global symmetries relate to diffeomorphism symmetries, and diffeomorphism is gauged. and therefore there's no other symmetry. So everything is automatically gauged in string theory. Every symmetry you get. So this is what I just told you. The charge falls in, and then if the black hole disappears, the charge disappears. That's the violation of charge. So all the charges. So that's the condition for the fact that there are no global charges. Now all the charges in the spectrum appear. Well, there are two ways to argue this. There is a way to relate criteria 2 to criteria 1. In fact, a lot of these swampland conditions, one of the things we like about is actually relate to each other. They are not independent, and that reinforces each other, so we believe in it more because it's it forms a cohesive collection of things. All charges, so taking U1 for example, symmetry, as I said, it has to be gauged by criteria 1. And now I want to argue that all the electric charges appear. There's no gaps in the electric charge. You cannot have only the charges of multiple of 2, let's say. You can have that 1, 2, 3, all of them appear. Well, suppose they don't appear. It turns out if it doesn't appear, you can define a Z2 symmetry. Based on that, in the corresponding quantum theory, which takes advantage of the fact that the odd ones are not there, and therefore you go back to criteria 1 and say, I have a global symmetry, and then there's a problem. So that's one way of trying to argue this. But there's another reason, and again, it goes back to black holes. Why is that? Why is there a black hole? Well, the black hole argument is relatively straightforward. Pick a charge. Pick a black hole with that charge. Well, Bekenstein-Hawking tells us there's a huge number of them, in fact. Area over 4. You cannot have gaps, because there you can write a black hole solution. So either the Bekenstein-Hawking entropy is incorrect, or if it's correct, that means it's occupied, period. So you cannot avoid having charge. It's like saying the black hole with that charge is not allowed, but there's no reason you can write a black hole solution. So therefore, the existence of a classical black hole would suggest that, and interpreting the black hole entropy as such, implies that you cannot have a gap in your charges. There's no reason some charge can be skipped, because the black hole makes sense. There's nothing wrong with the classical black hole. So this is, again, a black hole argument. As you can see, the black hole runs the show. Okay, so now I come to the third criteria. The range for fields is finite. So consider a scalar field, a good old scalar field. We study quantum field theory with the simplest example is a scalar field. Take it, and usually we take it to be going from a real field, going from minus infinity to plus infinity in terms of values. The claim is that the range of it cannot be so, and indeed the range of it is less than m Planck.
Aren't some models of inflation violating this?
We come to that.
But the answer is yes, right?
There are some models. The question is whether all models are not. But yeah, there are some models which violate this. That's correct. So we do not have a deep explanation of this fact, but it's based on observations and examples of string compactification. So let me actually say what I mean by that. In fact, this is not quite right, what I'm writing here. The field range can be infinite, but what happens is that if you go to the farther distances than m Planck, it turns out that you invariably get light states. That means if you take an effective description of your system, where you say I want to ignore all the states with a mass bigger than a cutoff, then you're restricted to a finite range in field space. Because if you go with a bigger range in field space, the masses of the particles that were higher than your cutoff become light and enter your spectrum, and your theory breaks down. Your effective field theory has to be modified. So for a given, no matter what the range of masses you pick, for a given effective field theory has a finite range. In other words, there would be, if you go in distance delta phi in field space, you get a tower of states coming light, which go like exponential minus alpha times the distance in field space over m Planck. So if you go like 10 times m Planck, you get things which are e to the minus 10, and so you quickly hit the problem. So this strictly does not say that you don't have a finite range. It means that you better then take into account the tower of light states which are going to hit you. And this would also be a problem for inflation-type models, because in that context, you don't want to get the tower of light state coming in, because you create these light states as you roll, for example. So this is a problem no matter what. So effectively this statement translates to that, okay, this is not a strict statement. There could be a constant, but roughly of order 1. This alpha would be some order 1 number, which determines what it is. What is that alpha? We know in string examples, this alpha is very close to one different example, 1, 1.2, 0.8, whatever. We don't have a precise number because it depends on models, and we don't have a lower bound or upper bound. So this is at the level of some order 1 number, which you don't exactly know. All the string compactification look like this. What does this mean? Well, in string theory, this has a dramatic implications, because in string theory, what are these scalar fields? Where do we get these from? Well, these correspond to the sizes of the internal manifold, like the size of one handle and this shape or that shape. And you can say, I can stretch it this way, that's the field phi getting large this way, or I can squeeze it the other way, the field going the other way, and so on. Each direction corresponds to changing that shape or size of the internal space. You can think of it that way. So what we are saying is that when you go to extreme corners, when you go large distance away from the middle, you'll hit places where you get the light states coming down. And that's precisely the region where the description breaks down and a new description comes in. And these are precisely the bread and butter of duality in string theory. Duality means that you have to change your perspective. You have new light states, you have a different description. The dimensions change. In fact, as you go in field space, your description is so bad that you thought you're in 8 dimension, maybe it becomes 9 dimension, or it becomes 7 dimension. So that the tower of states will change your perspective completely about what's going on. So that means that in each region you have a patch that you can really talk about as a given field theory of some effective description, but as you approach these large distances away, your description breaks down and you have to come up with a good description. These are the tower of light states.
What type of duality, like S?
All dualities, T duality, S duality, you name it. I'm being very general, so in this context it includes all of them. So this is the bread and butter of duality. That is, if you want to get a dual description, go large field space. That's the way to think about it. There's no way you can miss it. Just choose a point and go far and just walk after a while you get there. That's the lesson that this is telling us. Extended objects. So string theory is a theory about extended object, whether it's one-dimensional like strings or membranes like M-theory and so on. It's a theory of extended objects. But I claim that this is actually related to the fact that the field space is finite in range for a given effective theory. How is that? Well, let me explain why that's the case. Start with any theory, let's say a theory, even in 4 dimension. Compactify it on a radius of a circle. So take a periodic box of a size r. Okay? Since we are talking about quantum gravity, the radius field will be dynamical field. It's a part of the metric component. So if you write down the degree of freedom of it in terms of the lower dimensional theory, one lower dimension, you get a Lagrangian which includes grad phi squared, where phi is related to radius in this way. So you can think about phi as a scalar field in one lower dimension, where phi controls the radius of the circle. Now, consider phi much, much bigger than 0. Well, that means radius bigger than much bigger than 1, right? Phi much bigger than 0, it means the radius is big. So compactify the theory on a big circle. From the viewpoint of the lower dimensional theory, you get a tower of Kaluza-Klein states. Namely, there will be momentum modes that can go around the circle, whose energy go like n over r. From the viewpoint of 3D, these are very light if the radius is big. So as phi becomes much bigger than 0, the theory breaks down. What does that mean? Well, the effective theory was 3-dimensional. For a large radius, it becomes 4-dimensional. That's, of course, not a big deal from the 4-dimensional perspective. It's obvious. But this fits very nicely with that statement that phi cannot be too big. If it's too big, it means that you lose the 3-dimensional perspective, it becomes 4-dimensional. But you might ask, okay, what about phi going to much less than 0? Because phi goes, as you can see, phi can go from -infinity to +infinity. And I told you, you can go any direction you want and you're going to hit the duality. Is it true? Let's go phi to -infinity. If phi goes to -infinity, radius goes to 0. If radius goes to 0, all these momentum modes become very massive because they go like n over r. R is going to 0, so they're very heavy. So you can ignore them. So you might think that the theory is fine. So if you just take an ordinary theory of gravity with no extended object, compactify it on a circle, you can go to a circle going to 0 size, and the range of field will be infinite. So that would be a counterexample to this statement. That is, if the gravity by itself had no extended object, you could easily have an infinite field range with no problem, which is not the case I claimed in the criteria 3. How could that be possible? If you take the size of the box smaller, how could you get light states, which you didn't have before? The only way is that the sides of the box are now feeling some topological effect that you can go something from one side and come back the other side, which used to be heavy before. These are extended objects. So that's what happened in string theory. That is, the light states emerge when your circuit goes down by looking at these wrapped strings or winding strings from one side to the other, and these are the light states which break the symmetry of the theory being Okay, so therefore again, we lose predictive power for looking at the three-dimensional one, and that's the dual perspective. So just saying that the scalar field range is finite is almost equivalent to saying you must have extended object in your theory, and therefore gravity. So if you believe that's a maxim or that's the principle, then you're almost forced to have extended objects in some description, some form or another. Okay, so I already explained this. These are the KK modes became heavy, but then you have string extended object, and this is one of the ways we discovered dualities in string theory. So the next criteria is that gravity is the weakest force. Now, it has been observed looking at all these landscape of string theory that you do have in all these different things. You have charged, electric charged particles. But what happens is that we have found that always the force between them is always stronger. The repulsion force, here denoted by this red line, is always stronger than gravitational attractive force between them. That's just an observation. So in other words, in the fundamental units, if you take M Planck units, the mass is less than charge. Well, can we explain this? Well, first of all, what is the reason for this? Well, it's observation. So we can come up with some kind of explanation, again, using black holes. So let me try to explain that. So this is a kind of, again, heuristic, but nevertheless, it's instructive to go over it. You take a black hole and take the extremal case, Q equals to M. Now, as I said, black holes evaporate, even the extremal ones, if you assume non-supersymmetric ones, which we are assuming now. So take a non-supersymmetric one, and take Q is equal to M. Therefore, it has to disappear. Now, if it disappears, it has to do by emitting objects, like charged objects and masses and so on. But how could it do this? Well, if it emits a tiny particle of charge Q and mass M, the charge goes down to Q minus Q, and the mass goes down to M minus M. But we know that for the black hole cannot be super extremal. It should be sub-extremal. That means this better be less than or equal to M minus M, which means the thing that we emitted goes the other way. That is, the mass of what we emitted should be less than its charge. In the extreme case, should be less than or equal to its charge, and we know that equality can sometimes be arranged also. That's the BPS cases. So that means that the statement is that the mass is smaller than charge is kind of related again to black hole properties. So this is quite remarkable that this is the case. Now, there has actually been recent work on this, since the people here are familiar and follow the GR story. So let me explain some further evidence for this. So, this was just motivated from string theory, but the question is, does it have any other wider kind of thing beyond string theory that we can see examples of it? For example, in GR. So in the context of GR, Horowitz and Santos et al. Looked at the following problem. They looked at GR coupled to Maxwell's, just pure gravity coupled to a Maxwell field. And they found that this problem, this theory, if you have sufficiently strong electric field, you get naked singularities. You can develop something which initially has no singularity, evolves in time to get naked singularities, violating the cosmic censorship. So we suggested to them that actually it might be, we asked them whether they have included the effect that there, first of all, since it's the U1 field, the spectrum must be complete, so there must be charge state, that's number one. Secondly, the mass of those should be lighter than the charge. Have they taken into account the fact that if you have a U1, you cannot have a constant theory of gravity without charged particle whose mass is less than the charge? They hadn't. So we suggest that maybe this cosmic censorship violation might be modified if they assume there's such a particle. They said, okay, let's consider a varying mass particle, mass anywhere value, and see whether or not we can get rid of this naked singularity. They found that as the electrical field gets bigger and bigger, if the mass is exactly less than charge, exactly equal or less, then the electrical field gets shielded by creation of these particles, and you don't develop the naked singularity. So this was dovetails with cosmic censorship without being built into it. It solved that problem. So there are these kind of evidences that people have that makes one believe in these kind of things beyond, the examples that we have dealt. And there are other reasons on it, but that's the kind of thing that give us further evidence. This is, I told you about this one. So you can also extend the weak gravity conjecture from particles to membranes. That is, if you take the membranes of extended objects, the gravitational attraction between them due to their tension is always less than or equal to the repulsion based on the fact that they're always charged. Now, it turns out, as I said, the only case where they exactly balance is the supersymmetric case. But in any other case, they're not balanced and one of them wins. The gravity is always weaker. This suggests that no non-supersymmetric anti-de Sitter exists in string theory. It's not a proof again, but it suggests. Why is that? Well, at least the way we know how to construct anti-de Sitter spaces in string theory typically goes by, you take the parallel collection of these branes of various kinds, and the electric repulsion between them exactly cancels the gravitational attraction, and so they are stable. They just don't move. And then you go to the near horizon geometry and you get the ADS description. That's for supersymmetric one. But if it's non-supersymmetric, the claim is the electric repulsion is much stronger than gravitational attraction, and therefore they will all fly apart. So there's no way you can balance it, and therefore there's no way you can go to the near horizon limit with a stable ADS. So ADS, non-supersymmetric anti-de Sitter space, is not stable. It's not there. And there are similar statements that people have used the weak gravity conjecture to learn something about mass of the neutrinos and the weak scale being related to this that I don't want to talk about right now. But anyhow, the weak gravity conjecture has found different applications in particle physics and GR and all that. So there's a lot of evidence emerging in different ways. Okay, and so now I come to the more recent stuff that, yes.
This M less than Q business.
Yes.
So if I visualize a Planck mass particle
Yes.
with an electron charge,
Well, so the point is that this point is that we don't imagine it as a point particle. So if you have a mass less than m Planck,
okay,
so the conjecture says that there should. So when we talk about Hawking radiation, we mean that there are massive objects with masses less than m Planck.
yeah, but let's take the limit. Let's say I have a particle that's almost Planck mass, and I give it an electron charge. How close is it coming to your limit?
So the statement is that the bound should be strictly m. First of all, the bound is not sharp. It says that there is a charged particle whose mass is less than charge, but mass is less than m Planck. The exact value is not precisely stated, but less than m Planck. So let's say 1. However, this whole description breaks down because the black hole of size m Planck is not. It cannot be described by a GR solution. We don't trust it anyhow, because the horizon curvature and all that is Planckian, so we don't trust the class 2 black hole description. So that's a borderline that we cannot say much. But you're asking a good question. You're asking about it, what's the precise version of it, and we don't have.
Okay.
In fact, some of these criteria, as you can see, are not as precisely formed as they could potentially be. Again, it feels like similar things that you might have when you teach quantum mechanics or Bohr-Sonnenfeld quantization rule and all that. Can you say precisely? Well, not exactly. This is similar. These are similar in that spirit. So there's something true to it, but I wouldn't say this is as precise as we'd like to say. I agree.
But someone could look for an example that violates any of these in principle.
Yes,
And nobody found
even in string theory.
In string theory.
Yeah,
Nobody
yeah.
found them.
Well, not yet, but they could. I mean, that's the beauty of it. You can try, you can go and construct an example where it's reliable, some values are weak, and you can compute it. Say, sorry, your conjecture is false. That would be perfectly fine. And that's the name of the game here. That is, we looked at the examples that we have studied, but that's not complete, and we cannot claim that these criteria are absolutely correct. The more they are connected together, and the more whole they make as one object, is more believable, obviously. But I would say that we should look for errors. We should look for disproving them. I think that's how we will make sure they are correct or not. So this is the last topic I want to talk about, the relation between cosmology. So this is actually the most difficult area to talk about, unfortunately, despite the fact that this is the most interesting one we want to talk about. The relation of string theory to our universe, that's the one that Avi also likes. So what can we say? What are the lessons to say there? Well, this is the usual kind of picture. I don't know who drew this. I'm just stealing it from somebody. WML, thank you. Anyhow, I stole it from somewhere, but this is the kind of picture you see. You have probably something expansion at the beginning. People typically talk about it as inflation, and we are expanding now. It's going forever, it seems, or doing something, and it's now just accelerated expansion has started a few z values ago, and so we are undergoing accelerated expansion right now. Okay, will it end? That's one question. string theory landscape, what do we know about it? Well, the only universes that we have been able to construct in that landscape that last forever have a property called supersymmetry, which our universe does not enjoy.
Does forever mean both in the forward and the reverse time direction, or just?
No, I'm talking about forward right now, but we'll come back to the reverse direction in a second. So you could, in this context, you can ask the question is that you have a solution which does not depend on time period. So yes, either way. Can you have a situation which doesn't change, constant, time independent? Do you have any solution in string theory which is time independent? The only examples we have found which do not have any time in them is supersymmetric. Otherwise, they always seem to decay to something else.
Even just pure vacuum.
Pure vacuum without supersymmetry?
No, just no content.
No, content for us. So you have to say how you got that no content. In other words, we cannot. That belongs to, no content belongs to Swampland because everything has a graviton in it, for example. So no content doesn't exist. Period. We're talking about quantum gravity here. So then the question is, okay, just graviton? No, that is also we believe might belong to Swampland and so on. So what are the possibilities? That's precisely where not all your imagination. You cannot make the imagination go completely wide. Not everything is allowed. Anyhow, so it seems like the only examples we have found which can last forever, which means they are stable, which don't change with time, they are supersymmetric, and we know our universe is not one. Therefore, we have to understand what happens to our universe. So supersymmetry, as you know, is a statement that you have equal number of bosons and fermions. If the left one is boson, right one is fermion, and we know that that's not a symmetry of our universe. But for supersymmetric ones, they're so nice. They allow Minkowski space, or something very close to our universe with zero cosmological constant, or anti-de Sitter with negative cosmological constant. So these are really the only examples that we know of how to construct in string theory which are absolutely stable. Exactly zero cosmological constant or negative. From the get-go, we are in trouble. We are not in supersymmetric case, and the cosmological constant or dark energy appear to be positive. Yes? No? I think you're asking a question. Okay. Good. So this is some properties of ABS, but we know that this is not observed. The partners of the particles are not observed. Supersymmetry is broken. So our universe will not last forever. If you take this as a principle, which we do, so this is another conjecture that the only stable solutions are supersymmetric. So therefore, we immediately learn that the fate of our universe is going to be some instability in one form or another. The question is, what is the form of instability and what is it going to be? Well, how long do we have? Let's see, 10 more minutes. 15 more minutes, so let's see. Well, this is some crude scale. It's nice to be able to put it all together in one arrow and so on. Well, before I talk about timescales, let me remind you, our universe has dark energy, and the dark energy leads to a natural timescale, which is an appropriate unit. It's 1 over square root of that energy. In suitable units, that's a well-defined thing. So it gets a natural time unit from the dark energy.
But that's very short. 10 milliseconds.
No. Dark energy. Dark energy
is a milli-electron volt.
So this is big. 1 over square root of it, right?
Milli-electron volt?
You're doing in Planck units. So this is like 10 to the 60 Planck lengths, Planck times.
It's a Hubble time, right?
Yes, it's a Hubble. I will show you in a second. So this time is 10 to the 11, about 10 to the 11, depends on whether you put pies or no pies and so on, but anyhow. Our universe is about 10 to the 10, and this number is 10 to the 11. That's interesting. So the dark energy is coming something close to the value we are in. It's related to the fact, by the way, it's not a mysterious statement, it's related to what sometimes people call coincidence problem. It's a different version of casting the same question. We happen to live an interesting time where the dark energy scale is related to the time scale we are on. That is another way of saying that dark energy has just become relevant and so on. So what is the reason that we have this? What is the meaning for this coincidence problem? It could be coincidence, that's the way it's called. And we have a long way to go. For example, the proton decays happened 10 to the 35, we have a long way to go, no problem. So luckily we're going to cross this region, it seems, maybe. But is this a coincidence, you might ask? This sounds a little too suspicious. Well, how about non-supersymmetric version of this system? Because we live in non-supersymmetric world, and we therefore ask, what is the non-supersymmetric de Sitter? Why are we asking it? Well, because the popular model for how our universe is today is de Sitter space, and because we have a dark energy, lambda, and it's viewed as being constant, so it's what's called cosmological constant. Therefore, in string theory, there's no constant in the universe. There's always expectation value of some field. Therefore, we view the dark energy as arising as a minimum of some field. And we imagine having some field with some potential whose minimum energy value is the dark energy, no problem. So in string theory, you can contemplate this kind of situation, and we call this the de Sitter solution or de Sitter vacuum, and this sufficiently in the infrared behaves exactly indistinguishable from a constant cosmological constant. But why not rolling scalar potentials? Why don't we consider the dark energy to be changing in time? What if it was not at the minimum? All we have measured really now is, well, we have measured a few things, but we certainly know lambda is positive. But could lambda be changing in time, either back bigger or less or so on?
Even in the first case, you can have tunneling.
I'm coming to that. Yes, I'm coming to that. But at least locally stable depends on what's the potential value. Yeah, I'm going to come to that. But people did not like this kind of scenario for the following reason. I'm going to review why people did not like to view this alternative that you have a rolling field. Why didn't they like it? Well, the scalar typically will couple to some matter fields, and its rolling will lead to observable effects. For example, so we know that from z equals to 1 until now, the fine structure constant percentage change of this is very tiny, if at all. So therefore, if this field has changed significantly from z equals to 1 to now, and if it couples to f squared term, let's say, in some way, you would have thought that there would be some effect. Okay? So this looks a little bizarre that this field, if it is rolling, why hasn't it shown up in this kind of effect? So that's one of the criticisms. Another criticism is that the fifth force kind of issues that people have again studied in astrophysics context, that is, the coupling of the scalar fields to matter, since it's very light, you can show that the slope cannot be too big. It's very light. It should give rise to a fifth force between, different things. But this fifth force, this phi, couples to different fields differently. Maybe it couples to proton and neutrons differently, or this and that differently. So you think that it will violate the equivalence principle because it's not universal. But there are the people have checked this fifth force idea and to try to check for the violation of the equivalence principle, and there has been good strong bounds that this doesn't seem to be the case, which means, again, a negative kind of statement, so people do not like this kind of scenario because of all these strong bounds. But actually, neither of these are actually good explanation, good arguments. What these arguments show is that if there is a scalar field, it should couple strongly, as we know in string theory, to some fields, but not necessarily to the visible matter fields. The visible matter fields is what we are talking about. There are much less bounds on, let's say, the dark matter and other things. So the bounds get far weaker in any of those other issues. So the perfect possibility might be that if you view our internal geometry like Calabi like this, a particular small region of it can give our standard model, and another region of it can give us a dark matter, including this other scalar field. For example, that scalar field could correspond to the size of the matter which come from some other cycle over here. And it turns out that this kind of models can easily be constructed in string theory. There are models where these are kind of separated. So therefore, it's not a good reason. All we are learning is that this scalar field should couple with the standard model. In other words, that quintessence field better be part of the dark sector. And that makes a lot of sense because that means dark energy is also part of the dark sector. Sounds good terminology there. So both the energy and matter might be part of the same thing, kind of related issues. But there is another strange feature, you see. In fundamental units, the cosmological constant today is of order of 10 to the minus 122 in Planck units. But you can actually see that there is a problem if the potential has too much slope. You not only need V to be much less than this, or of this order, you need the slope of it in fundamental units also to be tiny. Oh, come on, how could it be that's the one and not be 0, right? You would think. But we made that mistake once, I remind you. We thought that V was, many people, like our field, people believed that, come on, something cannot be less than 10 to the minus 123 and 120 and not be 0, but it was, okay? This is an example. So you might have to think, wait a second, am I going too fast with saying that this means it's 0? Well, this looks like double fine-tuning for sure, but actually not so. You see, the bound is exactly of the same order. So it turns out if there's some reason that grad V is related to V in some form, this is not double fine-tuning. This is the same fine-tuning as that one. In other words, the minimum of the slope, if it's bounded by the potential itself, then that could be an explanation of why this is also could be parametrically small. So you ask, okay, what are the cosmological bounds on this slope? So in this plan of this part of the talk is that I want to argue that grad V is bigger than a constant times V. It's a new Swampland criteria, that slope, and C is of order 1 in Planck units. And the range I have already told you that is bigger, less than a delta, and I want to talk about the implication of the finite range of the field that I talked about, and this criteria. It turns out that the slope of the potential over the field, you can actually look at string models, because you can have the scalar potentials that generate in the string theory. What bounds do they give you? You find that in a very large class of string models, indeed grad V over V is bigger than some numerical constant order 1. That's reassuring. So in other words, the most obvious models you take have this property. In fact, there's a so-called no-go theorem, Maldacena and Nunes, that shows if you take the 11-dimensional M theory and take a 7-dimensional manifold, no matter what shape or things you take, as long as it's not singular and as long as the curvatures are not big compared to Planck scale, you cannot get de Sitter. That has been known for more than 15 years. People know this fact, that de Sitter is hard to get. But actually you can push it further and you show that so you might ask, why do people talk about de Sitter in that context? Well, they say, well, maybe it's singular. So the way to try to get de Sitter is to do something crazy. Namely, to go to Planck scalar curvature, say, okay, nobody said we cannot have Planckian curvature, we put somewhere there, and since it's hard, then we can maybe have it. Okay, so somehow nobody claimed that this is a strong restriction for de Sitter, it's just that de Sitter cannot be realized by big objects. But you can take that same example of the M theory in 11 dimension and show no matter what shape you take, not only grad V cannot be 0, but it's always bounded by a constant of order 1 bigger than V. So this grad V bigger than V is actually supported by string examples. So this is not a random coincidence, that is, at least we can prove it, that there is a bound and you can compute the bound depending on which dimension you're at. So for example, if you assume that whatever you compact to satisfies the null energy condition, you find that this constant in this equation is of order at least 1.2, order 1, which is similar to the kind of ranges that is experimentally allowed or not. Well, so now let me talk about applying these ideas to cosmology. Early universe, inflation has some tension with both criteria. The criteria being finite field range and also the grad V being too small. The slow roll parameter in inflationary models is given by 1/2 times c squared, where this c squared is exactly this c appearing in this formula. It's that constant. So that constant in the string models are typically 1 or very close to 1, and in inflation models, typically one takes these numbers to be very small. For example, a textbook inflation leads to epsilon is 0.004, and anyhow, so it's tension, right? You could say, well, this is still order 1, depends on what you mean by order 1. The string models typically. Sorry?
That's not order 1.
Well, okay, so yes.
Well, no, but I mean.
Okay, so I'm not going to make statements. I'm just saying that the conjecture does not have a precise constant, and so we don't know. We cannot say this is ruled out or not. But I'm just saying that the examples we know in string theory and all these really give you number very close to 1. In fact, it's very hard to get numbers less than 1, and we're still struggling to get numbers less than 1. Moreover, the number of e-folds being greater than 6 e-folds that we need for inflation leads to the range of the fields bigger than 5 in typical models. Again, people try to change this by multi-field case or this and that. So people have tried to avoid this, but this is again the typical story for
So
the
string theory violates inflation, is that what you're saying?
No, I didn't say that.
Okay.
Because I didn't tell you what delta is. I said delta is order 1.
Right, but inflation requires 0.0.
No, delta is, the inflation requires delta bigger than 5. Delta is the range of the field. There are two things. Let me just remind you. I'm talking about two conditions. One is the range of the field is less than delta, and the other one is the slope condition. So the inflation has C is 0.00 whatever it was.
So it does violate
Well, again,
the
if I said epsilon is strictly 1, yes, but I didn't say that. I said order 1. So I don't know. I wish I could say. This
So how
number
much
is
smaller
big.
than 1 will it rule it out?
Well,
if it's 10
that you should ask the inflation people, but I think typically, I think the inflation models will have C less than 0.02. But I think that people can become more creative in inflation models and multi-fields and this and that. So I don't want to. I'm not an expert on inflation, I admit. So I don't want to say what is rules of that or not. But anyhow, certainly it's tension. At the very least, it's tension with inflation models. I wouldn't say it rules it out necessarily, but certainly tension. And this is another tension. But 5, okay. 1, 5, okay. So this is less of a tension, but could be still tension. The first criteria is more of a tension. Now you could ask. What do we learn from looking at cosmology more precisely about what that constant is, C, in that equation? You find that if you draw this axis is the z-axis, and this is and this axis is the W for the matter, for the dark energy, I mean. So the value, so the allowed ranges from experiments is roughly between the shaded, is under the shaded area, under this black curve. These are all allowed. And W equals to -1, which is the cosmological constant case, is certainly allowed in that region, is perfectly fine. But you can see that if you take potentials of the form e to the minus c5, where that c is the same as the slope I was telling you about, c of order 0.6 is perfectly fine also. So c of order 1.6 is perfectly fine with experimental bounds. So that could be a possibility there, and if that's the case, and if the conjecture is correct, we better be finding that the potential should be changing soon enough. That is, we are going to have W measurement, which is of order now, of order -0.95, not -1. Or if it's lower, depends on how lower you are, you might be lucky or not. Again, it depends on what's the order 1. But to have it constant would be against this would be C0 down here. How about the future? Well, if we lived in the Sitter space, if the Sitter existed and the conjecture were false, then of course you can have, as Avi was saying, you can have an instability in the form of a metastable state, and this is many proponents of the Sitter space in string theory put this scenario forward, that the Sitter space is not completely stable, but metastable, and it will decay by some tunneling. But typically, this height would be much bigger than potential if it wants to be stable, and there is no reason there's any correlation with that lambda, and therefore you would imagine that the lifetime is much, much bigger, have nothing to do with this height. But this lifetime, I told you, the natural time scale we live in is right now 1 over root lambda. So this would not explain the coincidence problem. If you are in this scenario, it could decay sometime, we don't know what. There's no reason to decay in just the next factor of 10, for example, in Hubble time. But if you are in a situation that we are conjecturing, we'll be right now in a potential at this point here, and the slope cannot be too small. It cannot be staying there. It should be moving. And if it moves, two things could happen. Either it could cross 0, in which case the universe will undergo a phase transition, or if it stays straight, it will go a long distance. But again, if it goes a long distance, I told you if the range of the field is too large, you get the tower of light states coming down. So either way, you will have to cross a transition point. So you can estimate how long does it take to either cross or hit the light states based on these Swampland conjectures, and you find this order of Hubble scale. That is, the number of e-foldings in the future ahead of us is the ratio of those two constants that I don't know how to measure, times 3 times 2 over omega of the dark energy, 0.7. So this is of order 1 number. So then this conjecture will tell you that the universe will undergo a phase transition of one of the other type of order 1 in Hubble time in the future, and therefore the coincidence problem is not a coincidence. That is, we are only in the time span we could measure it, and after that we are gone. The universe will enter a new phase. So that's the future, and so with that I will conclude. The Swampland ideas are beginning to be sharp and extend and better understood. They define some universal properties of consistent quantum gravitational theories. They could have dramatic implications about our universe, but still a lot of work needs to be done. We're still at the very preliminary stage of this game. Some of them are, these criteria are very well established, some of them are getting refined, some of them are getting more predicted, corrected, this and that. So I think it's a long road, but I hope that I conveyed the excitement we have in this area. Thank you.
Questions?
So, in your argument for criterion 1 of the lack of global symmetries, you seem to assume that black holes would completely evaporate and would do so in such a way that all information would be lost. Wouldn't that imply violation of unitarity?
Yes, so
Isn't
good question. So people have used that argument to argue that if you take these light states, when these charged things come out. So they have sharpened the statement about using the exact black hole evaporation process to find that there's a problem with that scenario. So in order to put a large charge, you want to have a huge charge coming out at the end. It doesn't happen. So that's the kind of problem people need. But now you could have discrete symmetry like a ZN symmetry. That would not be ruled out by this argument. But then there are other arguments that I haven't told you about, using holography and so on, this and that, which say that that cannot be done either. So we have good evidence, we don't have a proof, that global symmetries are not there.
So about this non-supersymmetric string theories, sub-BPS counts, what is the progress? Are you able to count them? Are there interesting structures there, like sub-BPS counting theories, or?
Well, there should be, because the black hole entropy questions are always interesting. Of course, at the close to the bound, Q close to n, the black hole argument is going to break down because you have to be sensitive to exactly what's the correction to that formula. But if you take, for example, masses much bigger than charge, then yes, in fact, people have talked about that. In the context, the particular context people actually have written nice papers about is when you start with the supersymmetric one and then change it a little bit to non-supersymmetric one, and they have checked that that works correctly as it should. So the small change from the supersymmetric to non-supersymmetric one is consistent with Wittgenstein-like entropy.
So you argue that the current de Sitter state will not last very long. What makes inflation different that there we think it might have lasted 60 folds while the current one does not?
Well, no, the same thing.
So
I would say same
it's
issue.
the same thing.
It's the same thing. So
if inflation happened, then
that's why I said delta is 4 or 5. I think do you find 5 strange or not? So it's amazingly enough, the two issues are correlated. So we are relating the very past with the very future.
But if it did take place in the
If it
past,
did take place,
then
we
we
tell
can
you
do it
that
for another 60.
it would take, well, delta is 5. So you can actually, so exactly, so in our paper, I don't know if we said it or not, but you can actually say, suppose inflation did take place, then delta is bigger than 5, and then you can put it in that formula there and see what you get. So you can say, okay, put a 5 there, and the rest doesn't look that bad. So you see, that's the same thing could happen. So I don't want to kill inflation, I just...
By the way, stars live much longer than that, you know.
Yes.
Up to 1,000 times the present Hubble time. So the most common stars.
1,000 times the present, yeah,
The nearest star to the sun
I see.
will live 1,000 times longer.
I see. Okay, but as long as, yeah, so this certainly is
the stars will still be around.
By the time we go to the new universe.
No universe, just stars.
So yeah, the universe without star would be very boring, so that's good.
The coincidence problem you mentioned require delta V to be the same order of V, and the bound in your conjecture is a bound, the delta V. Is there any
That's
reason?
what you mean gravity.
Gravity, yeah.
Yeah.
So is there any reason in your conjecture gravity has to be approaching the bound rather than just...
Okay, good question. In other words, why are we close to saturating it?
Yeah.
I don't have a good answer to that one. It's similar to saying that suppose we believe de Sitter existed. Then you could ask, why are we at the minimum? We could have been rolling even if de Sitter existed. Right? So that's a similar question. Well, you would think that the thing would have settled to the minimum possible. So it's not unreasonable. So just as saying that the smallest critical value is allowed, rolling to the smallest allowed thing, meaning shallowest one, is reasonable. So it's not a proof, but I think it's not unreasonable to think that you're close to saturation of the bound.
Second question is, if W is -1, I would think the most natural case would be the forced vacuum case, rather than just a very flat potential, but very shallow potential rolling, but rather than just sitting at the
Minimum.
bottom of the
Yes.
minimum.
Yes.
So in that case, is there any consequence of your conjecture? I missed that part.
Yeah. So let me go back to this. So you're asking the question about
What's your
what's wrong with what's wrong? You're asking with this.
this one? Yeah.
Well, the thing that's wrong is that the gradient of v is 0, and this is less than. It's not bigger than the lambda.
Oh, you think this case is belong to Swampland?
I'm sorry. Yes. I've gotten into trouble with my colleague on this one.
So a quick historical question. And in the very definition of extended particles, are there scenarios where the extended particle is 2-dimensional, 3-dimensional, 4-dimensional?
Yeah.
Like instead of strings being 1-dimensional.
In field theory or in quantum gravities?
And quantum gravity.
Well, membrane theory, M2 brain, M5
so
brain,
those
these
are
are part of
actually-
the extended objects. So in 11-dimensional theory, we don't have strings. We have 2 plus 1-dimensional object or 5 plus 1-dimensional
I
object.
see. That's how to think about it.
So, weak gravity conjecture,
Yes.
that's great. Gravity is the weakest.
Yes.
Does it then also lead to any statements on the other forces?
Well, people have tried to use it in that context exactly, like electric forces for the other one, and then people have. So there's a
Relative importance of
renormalization group issue that you have to know in what scale you're doing this and so on. So you have to be a bit more precise. Charge runs and mass and so on. You have to understand which scale. And so people have said, and people have tried to deduce facts about weak gravity conjunction also for things like asymptotic free theories or this and that. So yes, people have talked about it. The point is that every scale where you can have visible charges, in that scale the corresponding mass should satisfy this condition. So then it will apply presumably to other gauge forces too, and there's no problem with
But
it.
it's mass still, because the mass is gravity.
Yeah.
I'm just talking about electromagnetic versus weak.
No.
Can
Oh,
we
I see.
have-
No.
can we have-
This doesn't tell you there's
It
which one
doesn't
is
say
stronger.
anything
No.
about that.
It doesn't say you one is weaker or stronger than the other.
Exactly, yeah, you can have both.
No, it doesn't say. But it does say that the charge cannot be stronger than gravity. So when they kind of unify,
Good, gravity is.
the fact that they unify near the gut scale and gut is less than
Less
incline
than
is great. Otherwise, you'd be in trouble.
Okay.
So that
But
predicts that there would be some gut less than incline if ever they got.
But at low energy, you could have any
Yeah,
ordering.
no order, no problem with order.
No problem.
No.
Okay.
Great. I guess we can thank Cumrun for the great.
Thank you.
That was great.
Yeah.
Just what we needed. And you told us that black holes are relevant.
Black holes are run the show, not more than run. They run the show. They run the show.
You run this one, right? More, yeah, wonderful.
I heard you used to scream at speakers, and this is bullshit. I heard he did a lot worse. I heard he was just like very applicational and well, that's what I heard.
There's also this huge
نه نمیگه بس در حدی که من گفتم میگه علتش در حدی که بلک هول داشته باشیم یه وقت پیدا کنه ولی نمیشناسه حتما میتونه شروع
I was going to ask him for
چرا فرقی داره برای
a
اینکه
half an hour of
نیروهای دیگه در اون کانتکست کار میکنن برای همینه که هایرارکی داره ماس لستن چارجه نه اینکه چارج لستن ماسه یکیشون قوی تر از اون دیگه همیشه تنها وقتی که میتونه یک سکیل بشن اینکه دیسکریپشن